kind of a simple one, but in LaTeX, is there a way to put those symbols for the different card, like the heart and the...
Yeah, it's / heart suit, diamond suit, club suit, and spade suit.
Okay.
Your mic isn't on.
Okay, so for anyone who was trying to listen to what I was saying who couldn't hear me, I just want to go through the homework questions, and then if there's time left, go through the statics and dynamics chapters. I think these are the next chapters, I think 4 and 5, if I'm getting it right. And the question was, how do you typeset the card suit symbols like in LaTeX? I think, what was it called, diamond suit? Like that. I don't know exactly how to spell it. If you search for LaTeX diamond suit, I think you'll find it. And if you really, really hate LaTeX and you can't use LaTeX because you just can't figure out how to do it, and you can find some other way to type it, that's okay too. If you really don't want to use LaTeX, yeah.
If you Google Detechify, there's a website where you can draw the picture of what you want and it will tell you how to type it.
Detechify. I've used that to some success. I don't know, it doesn't always do it. If you just write an arrow, it usually gets the arrow. But if you draw something complicated, sometimes I fail at Detechify. I guess if you really can't find the symbol you're looking for, you could just use some other symbol and just say, like, this is how I'm using these symbols. But it should be possible to find that. Any other questions about the homework, about how to do the problems? Or there's a Moodle question about how to do, I think the question was, what is iterated inductive definitions, if I remember correctly. Does anyone have an answer to that? What is an iterated inductive definition? So if I say, if I define the natural numbers inductively, so that's one inductive definition. It's self-contained. There's 2 rules, and I've written both of the rules. I guess I should name them. Now, let's say I make another inductive definition that uses this one as one of its hypotheses. So let's say I wanted to make a list of natural numbers. So I could say nil is a list. That's the nil case. That's supposed to be NIL. That's right. So in functional programming in this class, lists are basically 2 things. There's a nil case, which means it's the empty list. There's no elements inside the list. And then there's this case that people call cons for historical reasons. And cons always has 2 arguments. The element of the list, and then this thing which we usually call the tail pointer. The tail pointer, I think, is like, the reason we call it that is because that's how you implement it. This is a pointer to the next console or a pointer to this nil terminal thing. So if I want to write hypotheses for this to make it a list of natural numbers, what should I write? I need 2 hypotheses. Yeah? Mm-hmm.
And L list.
Yeah. So I'm saying recursively, the structure that this N has is this structure. And the structure this L has is the structure defined by these 2 rules. This definition that I made here is dependent on this one because one of the hypotheses is referring to this definition. So that's what iterated inductive definitions are. It's pretty simple. Just as you make definitions that depend on prior definitions, that's the idea. So I think the homework is giving you a definition kind of like this, but there's no natural numbers. It's about cards. And it's asking you to prove things based on the definition. Any other questions about the homework? I want to make one kind of important announcement.
Yeah, the homework, I'm having some problem with problem 3.
OK. Let's remind ourselves what problem 3 is.
Even and loss problem, I think it's about, see?
Cutting cards, it's called. Yeah.
Yes.
OK. Is there a way I can answer your question without giving you the solution? Or do you have is it about clarification or is it about just like how to proceed?
I think it's about how to proceed. I think that I may ask you after the class.
OK.
And what's this all about? Sorry, I was a little bit late for this.
Did you just come into class?
I missed the first 5 minutes. So what's this all about?
Well, I'm not going to go over it again, so
Okay.
just come to class on time. Did you have a question on 3.1, 3.2, 3.3, like 3.1?
Not really.
Okay. Does anyone have a specific question about the homework? Yeah.
So yeah, for question 3, if we're doing a simultaneous inductive proof, if we're trying to prove it just for one of the definitions, do we have to infer a property about the other definition? So like if I'm just trying to prove something for even, do I have to infer a property about odd in order to prove that?
Okay, that's a good question. So let's just review like how these things are defined. So it's defining even and odd natural numbers. No, it's defining even and odd amounts of cards in a deck, right? Okay. Let me do a simpler version just for the natural numbers. So I'll say z is even, and successor of n is even. And what should I write as a hypothesis if I want to characterize like the even and odd natural numbers? Now I'm going to define another judgment here called successor of n is odd if something, right? I'm going to make these refer to each other. So here I'll write n even, and here I'll write n odd. Now I'm defining two different things, a notion of evenness and a notion of oddness, but they refer to each other. So if I'm trying to prove a property about the even and odd natural numbers, I have to do induction over kind of all these rules together. That's the idea of simultaneous induction. So I might have a, let's see if I can adapt to what it's asking you to do here. The first question is, what is the induction principle? So what's the induction principle for these rules? If I'm trying to prove some property P, if I'm trying to prove for all n, some property P of n holds, for all n where n is even, let's say, is that going to be strong enough to, in other words, like if I'm just talking about the even numbers and trying to prove properties about them, will I have enough reasoning power to do it? I probably need to make some statement about the odd numbers too, right? So I might say, for all natural numbers, if n is even, that implies some property holds. And for all natural numbers, if n is odd, that implies some other property, q, I'll call it, holds. And that's 2. And the idea is that I'm trying to prove both of these statements simultaneously. Does that make sense? And the inductive hypothesis I get is that whatever property is relevant, like if I'm in this rule, in this case of the proof, and I'm trying to prove the property holds for a successor of n, where this is odd, I get the fact that p of n holds for n, right? So it's the same idea now, except we have multiple definitions and multiple sort of statements about those definitions, and we're doing induction over all of them simultaneously. I don't know if that answers your question, if you had a more specific question about it. No? Okay. Any other questions about the homework? The important announcement I wanted to make is that I kind of looked at the solutions and the problems, and I decided, I'm taking these, by the way, I'm taking these homework assignments from a CMU course. I think homework question 4 is pretty hard, so decide to make it extra credit. If you've already done it, then you've got extra credit. That's the one about the missing cards. The reason I'm making that extra credit is because it talks about all this stuff about binding and binders, which we haven't talked about much in class. So I think it's going to be hard for you to do that before Thursday, probably. So just focus on 1 through 3. And the first one is really just the whiteboard policy. Any other questions? So I have office hour right after this, so if you have other questions you just want to talk to me about one-on-one, I'll be there. If there's no other questions, I guess I want to go on to the next.
So what does the PFPL stands for?
Oh, PFPL, that's a good question.
I believe it's up here in question 3 or question 2.
This is the textbook. So it's an acronym for Practical Foundations of Programming Languages, I think.
Okay.
Yeah. Okay. I guess if you think of other questions that come up, maybe I'll reserve some time at the end. Oh, yeah.
I was just going to say, last time we sort of made it almost done with a proof.
Okay.
We're working our way through lemmas, but we didn't finish it.
No, there's a proof we didn't finish.
Okay. Do you want to try to do it again?
It would really help me to see
sure.
how it finishes.
Yeah, and by the way, if we do anything in class that you really think we should do it again more carefully, just let me know. So can you remind me what we were trying to prove? It was about these...
So then can you derive S of L?
Yeah, right. Does SMM imply that S of L is derivable? And I guess we should, so this is our theorem that we're trying to prove. We should write down the rules for these things again. So can someone remind me how S of M is defined? So first of all, these are strings of parentheses. Is an M. So we'll call that rule 1, I guess. Okay.
S is M.
Okay. Now define S of L. I think there's only 2 rules for this, right? I think it has the empty rule, as I recall. Let's call that rule 4. Okay. And we did prove a lemma that said something about concatenation, right?
I think that was the part that we liked.
Is that the part that we...
Got to the end too, but everyone had questions about one of the last steps.
Okay. So that's the proof that we should do.
I think so, right?
Or maybe we should do both proofs.
Yeah.
Okay, so that was this. Let me write this statement again. So it's not quite this statement. We're trying to prove this, and then in the process, we decided that we needed another inductive proof about if S1L and S2L, then S1, S2L. Is that how it was stated? Yep. Of course, I'm doing the thing I usually do where I write way too big. And then I think we tried 2 different ways of doing this. One where we were doing induction on the derivation of the first one, and then derivation of the second one. And the first way didn't work, right? And the second way started to work. OK, so let's just start again. We're doing induction over... How do we get another pen color? I don't know. We're doing induction over this thing. So what are the cases of this? There's 2 of them, the empty one. So it could be that we've got rule 4 here. This is empty L. And then we're trying to conclude that this is derivable, S1, S2L. So I think the trick here is just to notice that S1 is the empty string. That's given. Sorry, thank you. Keep wanting to do induction over the first thing. S2 is empty. And S1, S2, sort of concatenated, I'll write this caret thing here, is then just S1. And we can write by the definition of concatenation. OK, and then that means that what we're really trying to prove is that S1L, but that's given too. So I just want to start there to say that we're done. When I typeset these things, I always have like a hand that points at the result, that's the thing I was trying to derive, but I can't draw a hand very well right now, so just draw an ugly star. Okay, and then what's the other case? We're using rule, I forgot to label it, 5. Okay, so what does our inductive hypothesis tell us? It tells us that the property holds for these two, right? I goofed up. Can someone tell me how I goofed up? I wrote S1, S2, S1, S2, but we've already got S1 and S2. So this whole thing was supposed to be S2. So the usual way to fix this is just add primes. Okay. So far, so good. Is anyone lost at this point? It all makes sense? Now, what are we trying to show in this case? Well, this whole thing is S2, and we're trying to show that S1, I can't write parentheses because I have some sort of special meaning here. I'll switch it this. How do we know when we're done in this case? We're trying to show that, again, S1, S2 is derivable in L, but now we know that S2 has some structure. S1, S1 prime, parenthesis, S2 prime is L. All right, TS for, that's what we're trying to show. Does anyone have an idea? Why is it by the inductive hypothesis? So, does everyone see that it follows from the inductive hypothesis? Maybe it would help to say how we're using the inductive hypothesis, like what's plugging into what. Does that make sense? So, how am I sort of dividing up this string to apply the inductive hypothesis? Well, this S1 is just S1, right?
S1, S1 prime is an L.
Yeah, that's right. Sorry, I'm goofing this up so bad. S1 prime. Sorry. That's just S1. Okay. So you're saying to apply the inductive hypothesis to this part, is that right? Okay. And then what does that tell us? That that's an L? Yeah. Okay, so we can say S1 prime is an L by the inductive hypothesis. Now what do I do next? I'm trying to be sort of really explicit about all the steps of the proof. So far the only step I've taken is just apply the inductive hypothesis to S1 and S1 prime. But I haven't yet gotten this thing that I'm trying to show yet, right? There's another sort of simple step I have to do. Yeah.
S2 prime is an L, which is given, and then you can apply rule 5.
This is given. Okay, so this is sort of step 1. Step 2 is to notice that I have this other thing that's already given to me, that S2 prime is an L. It's given right there. There. So the final step is just to apply the rule. Rule 5. So now we have S1, S1 prime, S2 prime, L by rule 5. There's basically just 3 steps there. Is anyone lost by that, or should we go through it again? Yeah.
I didn't get where you said S1 prime, L by inductive hypothesis.
Yeah, this is the trickiest step. So the other steps make sense, right? If you sort of somehow get this, then this is given, and I just apply this rule.
I got 2 and 3. I don't get 1.
Does anyone have a better explanation than me as to why this inductive hypothesis applies, or what's going on in this step here?
What inductive hypothesis are you referring to?
Yeah. Okay, so we wrote this statement, this theorem statement, and then we started doing this proof here. And the way to think about the theorem statement is that there's these hidden quantifiers here that say, for all S1, for all S2, if we can make this derivation of S1L and another derivation S2L, then what this theorem is basically doing for you is constructing a third derivation, this thing. So you can think of it as like a function you're calling in like a kind of functional programming setting. So this function is recursive. It's taking arguments. These two derivations are its arguments. And then it's producing a derivation as its result. So here, when I say that this follows from the inductive hypothesis, what I'm saying is I get this thing as a result, and I'm plugging in something for S1 and S2. So I think if I'm...
So you can plug S1 prime into where S2 is. In the,
yeah,
okay.
Yeah. This is the way I think of it, is that I'm kind of taking these two things, and I know that S1L, because that's given, and S1 prime L, because that's given. So I have these two arguments that are sort of in the right form, and they're juxtaposed just like this. So when I get out the result, it's the result I want, I guess. So the step that I kind of glossed over is this step of saying the argument is going to be S1, and the argument is going to be S1 prime. Does that make sense to everyone?
The given and subderivation is the same meaning?
Say that again?
The given and the subderivation is the same meaning?
Yeah, so if I write given here, or if I write subderivation, I think subderivation is probably better. It's just longer, so I didn't write it, yeah. Does everyone see why this is a subderivation? We're in this case, so this is our derivation, and this is the root of the derivation tree. And these are two branches coming off. So these are also subderivations. Yep. Yeah, so what he's saying is that maybe a better thing to write here is subderivation, if you had room. Any other questions about this proof? Yeah.
Could we, I'm having trouble sort of relating all of this, sort of down in the weeds stuff with proving the original proof.
So we were trying to prove this, and then we got sort of stuck with this other proof that we're doing. So maybe we could go back to the original proof. Maybe, let's see, how am I going to do this with? Is it okay if I change this whiteboard? I want to leave out the other one. I'll write this theorem statement again. SM implies SL. I think the case we're in is this one, right? S1, S2 is an M. If S1 is an M, S2 is an M. I think that's rule 2, yeah. This is rule 2. Oh, so what I'm trying to do in each of these cases, right, is construct a corresponding L derivation. So here, what do I have as subderivations? I have that S1M. This is a subderivation. S2M is a subderivation. And what I'm trying to get is an SL. So first of all, when I apply the inductive hypothesis to these two subderivations, am I allowed to, first of all? Does the inductive hypothesis apply to these two things? Yes. Why does it apply?
For the hypothesis is that whatever's an M is an L, and we get to use that on subderivations.
Yeah, you should think of it as basically what you're given in each of these cases is that the property you're trying to prove holds for these hypotheses, and you're trying to prove it now for the conclusion. So these are subderivations, which means we can apply the inductive hypothesis, which means if we do it for the first one, S1L, that's by inductive hypothesis, S2L by an inductive hypothesis. And if only we had a rule that looked exactly like this for L, we'd be done, right? If we could just take those two things and plug them together like we did with M's. But there is no such rule like that. There's this kind of, just these two rules. And this one doesn't quite work. So that's why we went off and proved this other lemma. And what does the lemma say? write it again down here. That if we have S1L and S2L, that's a 2, then S1, S2L. It's exactly what we need in this case, right? So I can say S1, S2L by, I'll just call it the concatenation lemma. And now I've got exactly what I wanted. That matches that, except I've basically replaced the M with an L. Any questions about that case? Yeah.
So you're saying the S1L and S2L because the theorem or the inductive hypothesis is that if S is an M, it implies S is an L.
Yeah, exactly. So I'm doing the same trick again where there's a kind of hidden for all quantifier that says for all S, if SM is derivable, then SL is derivable. And on this line, what I'm doing is I'm saying basically let that red S be S1. Here I'm saying let that S define it to be S2. I don't often write that, or people don't write that, because it gets a little confusing. You're saying S is equal to S1? Well, it clearly isn't, because S is this whole thing. You know, it's the same sort of thing when you're trying to teach students how to program in a functional way. So they're calling a function, and they're passing in an argument that's maybe smaller than the argument they have now, like you're writing factorial or something. And it's confusing because you're plugging in a variable for itself, but you're changing it. That's the same kind of idea. So I don't know if this is clear or not, or I can try to explain it a different way. Does it make sense? Yeah. What about the last case of this proof? There's this case that we haven't done yet, or we haven't redone yet, where this is the rule. And now I'm trying to derive that this thing is an L. I guess I could do it on the next board, probably. I can have that S is an M. This is the third rule. And I'm trying to show in this case that that's an L. So, I mean, the usual formula is like just see what subderivations you have. So SM is a subderivation. I shouldn't call these things all S's, I guess, because that thing was called S, so I'll call this S prime. Okay, so SM is a subderivation. And then can I apply the inductive hypothesis? I can, right? So what does that give me? S prime L is derivable by the inductive hypothesis. Now I went to the other board, but there's this rule. We don't quite have the rule that we want. There's no rule that looks exactly like that for the L derivation, but we do have this other one that says S1, S2, L, if both of these are L. And this is rule 5. So how can I justify applying this rule to this? Yeah, I can basically say that this one is empty. So if S1 is empty, then I can also say, I mean, this rule isn't part of our rule system, but it could be. I'm just taking this rule and replaced S1 with empty, which is OK because empty is a string. And if I apply this kind of modified version of the rule, it basically exactly matches what I want. It allows me to put parentheses around the outside of the string, so I can say S prime L by rule 5. And that's what I was trying to show in that case. Any questions about this proof? No? Okay. I guess circling back to the homework, does anyone have any other questions about the homework? Okay. So I guess in the remaining time, I wanted to start making some progress through the statics and dynamics chapters. We probably won't make it through all of them. There's quite a number. I guess there's 4 chapters in that part. But I just want to start doing it. So maybe the easiest thing to do is to actually bring up the textbook. That's not what I want. So this part 2 is the next thing to talk about, statics and dynamics. So let's just jump in here. Did anyone try reading this chapter yet? Or at least looking at this page, this figure? Okay, maybe a couple people. What is this saying? I guess we haven't really talked about the book's notation in class, so I want to make sure that it's not confusing to anybody. I don't know if people can read it. I might have to make it bigger. There we go. I think there's a way else where I can write right on this thing. I don't know how to do it right now. So what these chapters are really about is trying to introduce the idea of what is a formal semantics for a language. We spent the last couple of times talking about inductive definitions and inductive proofs because that's going to be the main technical tool that we use to give a formal semantics. So there's going to be syntax for whatever programming language or system we're talking about. And the syntax is going to be a bunch of inductive definitions, basically. And then there's going to be, at least in this class, there's going to be what we call a statics. It's also referred to as a type system. And again, that's more inductive definitions. And then dynamics. So has anyone used a language that has a type system? I assume almost everyone has. Right? Did you like the type system? Maybe not. Maybe you did. I guess one of the points of this class is that type systems are the mechanism by which you sort of describe abstractions in your program. So if you don't have a type system, it's hard to describe what those abstractions are because you sort of don't have this language of talking about abstract things. So I really think of this as defining the notion of abstraction in a language. And then what is the dynamics for then? Well, it's basically to say what the program does. It's to answer the question, if you think of the program as being something that does something, it answers the question, what happens? If you think of a program as some mathematical object that's equal to other programs that do the same thing it does, then the dynamics is answering the question of what programs are equal to other programs. And compilers care about that sort of thing, for instance. If a compiler changes the dynamics of your program so it does something different, like it used to sort but now it doesn't sort anymore, then the compiler basically has broken the meaning of your program. So both the type system and the dynamics are really about meaning, but the dynamics is really about concrete meaning, like what actually happens when your program runs. And the type system is about what is the sort of abstract meaning of your program before you run it. So people often think of type systems as occurring before you run the program, and the dynamics is saying what actually happens when you run the program. And all of this stuff is going to be given with inductive definitions, and if we prove any properties about it, it's going to be with these inductive proofs we've been doing. That's kind of the point of studying all the induction. Okay, so this first page here is just saying what is the statics of the the syntax of the language. There's two syntactic categories he's defining, types and expressions. And he calls these things sorts. This chart defines two sorts, tip ranged over by tau and exp ranged over by e. Is anyone confused by that, what he's talking about? When I first saw this notation, I thought it was a little weird. So the way I would write this, if I was trying to write this in a way that looks natural to me, is I'd write tau is either a num or it's a string. E is either a variable or some number n or some string s, or it's E1 plus E2. And he's got some other operators which I don't have to write. So you can add numbers, you can multiply numbers, you can take strings and concatenate them. You can compute the length of a string. Those are all sort of primitive operators on the data types in the language. And then the final thing is interesting. It's what he calls a definition. Let x be E1 and E2. And there's this more compact way of writing it that I'll use here. Let x. Oh, I did it wrong already. So does anyone have I think everyone has a sense of what numbers and strings are, what variables are, numbers, strings, adding. But what is this saying, this let binding, or what he calls definition? Yeah.
So if you see the variable x in the expression e2, then you just substitute e1, basically.
Yeah, that's right. So the way to think of this is, maybe in a more natural way of writing it is, let x equal e1 and e2, with a kind of line break there. This is a little more economical in terms of the number of symbols you have to write, but there's three sort of important things here. There's a variable x, there's two sub-expressions, e1 and e2. And the idea is, first we're going to run e1. e1 is going to terminate and produce a value. And in this language, what is that value going to consist of? Numbers or strings, right? So x is going to be either a number or a string, and then e2 can use x. So if I was going to write a program that, let's see, I guess the only thing we can do is really kind of add numbers, do things to strings. Does it have example programs? And it just goes right into the type system. Maybe it's better just to go right into the type system and just look at examples after that. I guess one thing I want to say is to talk about this. So he talks about these syntactic forms having arities, and he writes this arity of let like this, exp, exp, dot, exp, exp. Can anyone read that or kind of explain, like, what does that mean? So he says, I keep goofing this up. He says this has sort exp. Exp dot exp. Exp. Does anyone have an idea of what he's talking about here? Yeah.
Really, he's saying that like each one of those things is either a variable, a number, or a string.
Yeah, yeah, exactly. So there's kind of like these four occurrences of exp. Let's call this occurrence 1, occurrence 2, occurrence 3, and occurrence 4. And what he is saying is that this thing is an exp. This thing is an exp. The variable that E2 can refer to X is ranging over all possible exps, expressions. That thing is an exp. And then this whole thing, as a syntactic form, is an expression. But the important thing, I guess, is that a variable and a sub-expression are not quite the same thing. So he has this notation of dot. And that what this dot is saying is that basically this thing is a variable. And the scope of the variable, the sub-expressions that can refer to it, are the things that immediately follow the dot. So he's saying that this sub-expression can refer to that one by using this variable x. So it's a very compact notation, trying to say a lot of stuff, but if that doesn't all make sense, that's okay. I don't think it's quite essential. Just wanted to explain it in case you came across in the textbook and weren't sure what he was talking about. Okay. Finally, some awesome simple rules. Okay, so let's talk about the type system of this simple language. I'm going to skip over I'm going to leave this up and then go to the next whiteboard here, and you won't be able to see the syntax. But I think that's okay. So there's this form, gamma turnstile E tau. We refer to gamma as the context, or typing context. This is still an expression, and this is still a type. So we're relating three things now. It's a relation between three things: a context, an expression, and a type. And I'll give you the syntax for these contexts. They're either empty, or it's some context followed by a variable with a type. Yeah?
What was the name you gave for the little sideways T operator?
Oh yeah. These things are called, if you want to pronounce this, it's pronounced as turnstile.
Okay.
And I think it's spelled something like that. You know when you go to the subway and there's like this thing that prevents you from getting a free subway ride? That's called the turnstile. And it sort of looks like a turnstile. I think that's why people call it that. So it's traditional, I guess, in logic that you have a bunch of assumptions you're reasoning with, and you have some conclusion you're reasoning from those assumptions. And you separate those two things with a turnstile. So people in type systems reuse them. So the context is kind of all of our assumptions about what variables have what types. And from those assumptions, we're going to conclude that E has a certain type. And people put a turnstile in between those things. Okay. So let's go through these rules, see if they make sense. So if I have a natural number, or a number, I guess we'll just call it a number, what type does any number have? Num. There's only going to be two answers when I ask what type things are, because T is either, in this language, T is either a number or a string. And that's the first. Oh, he starts off with the variable rule, but I think that's too tricky, so let's start off with the number rule. I'm just writing this rule, num n as type num. And it doesn't matter what's in the context here, because this number has no variables inside of it. It doesn't matter what the context is. There's no variables. Okay, so a similar case is, if I have a string s, what type does this string have? Stir, right? And that's this rule, 4.1b. What if my program just consists of a single variable, and I'm trying to give that variable a type, tau? How do I know what type it has? That's the point of the context. So I go in and look inside the context, and I'm going to use different notation than him. I'm going to treat the context as a finite map, basically. So when I write this notation, I'm saying I look inside of gamma, and I treat gamma as basically this map between variables and types. And somewhere in that mapping, there has to be x, and x has to map to some type tau. And if that all holds, then I can say that x has type tau. under gamma. Sometimes people pronounce turnstile as under, like I just did. So I said x has type tau under gamma. You can also say it the other way around. Under gamma, x has type tau. Does that make sense intuitively? Yeah.
What the equal means there?
What does equality mean here? Yeah, that's a good question. I think that's why he's writing it this other form where he doesn't have to put an equal sign. So he says, I think that's how he wrote it. Yeah. So one question here, which is a completely reasonable one, is how do I know when two types are equal? Well, in this type system, it's pretty simple. Nums are equal to nums, and stirs are equal to stirs, right? So as we go, we'll sort of see type systems which are way more powerful and expressive, where this notion of equality is kind of tricky. So another way of saying this is, well, inside of this context, there has to be a mapping of x to tau, and that means that x has type tau. And it's conventional to sort of write the mapping at the end here when you really mean that it could be anywhere inside of gamma. So no matter which way you write the rule, you're kind of like fudging some details, I guess. Here you're sort of glossing over what equality means, but here you're sort of glossing over the fact that x could be in some other position than the last variable in gamma. But people just kind of, another way of writing this, if you want to be even more careful, I guess, is sometimes people will say gamma 1, x tau, gamma 2, x is type tau. So I'm writing the same rule 3 different ways, and they're all saying the same thing. Now I'm being even more pedantic and saying, well, the variable could be anywhere inside of this context. There could be context ahead of it, context after it, and the variable could be anywhere. Yeah. But when I write these, in this case, all these things mean the same thing. Okay. Okay, now the other kind of operators are sort of similar. So if I'm trying to concatenate two strings, well, the first expression better be a string. The second expression better be a string. And then I can conclude that the concatenation of those two expressions is also a string. So you notice this is not like JavaScript or some other language where types just kind of magically convert between strings and numbers without you knowing. This type system says, well, there's numbers and there's strings, and they're two separate things. And there doesn't seem to be a way to convert one into the other, except maybe this rule. This is saying if I have a string, I can compute the length, and the length is a number. So that's, I guess, how I convert a string into a number. But it's not giving me
any information in the string.
Yeah, it's just ignoring the information in the string and just telling me how long it is. So it's not probably exactly what you want. There's no conversion operators in this language. So what about this last rule? This last rule is maybe the most interesting one. So if I'm trying to conclude this whole program that consists of this let definition has type tau for some tau, the way I do that is first I type E1 and say that it has some type, call it tau x. And now the whole point of this let is so that I can produce a value and then have that value be available when I execute E2. But now we're just talking about the types. We're not talking about execution. So the notion of the value of E1 is just this abstract notion of a type, either num, right? This thing is going to be either num or stir, one of those two things. Oops. And then I'm going to run, or I'm going to type E2 under the context where x has the appropriate type. So that's the typing rule for let.
You want x has tau sub x.
Oh, thank you. Yep. Any questions about that rule? Does it make sense? Let's do an example just to make sure it makes sense. Okay, so let's say, I'll write it down here. Let's make it black. Let's say that under the empty context, I'm trying to prove that, or I'm trying to type a program that says let 1 plus 2x dot length. Oh, that's not quite right. I made a mess of this. Let me just start over. Okay. So I'm using the let form. I'm using concatenation of strings. And then I'm using this length operator that gives me the length of a string. Now, I could have written this program in a simpler way, but then we wouldn't use all the cool typing rules, so I wrote it this way. Can anyone think of a simpler version of this program that doesn't use let? What if I just wanted to simplify this program and get rid of this let thing? Could I have the same program that does the same thing?
So you could just write len a cat b.
Yep. So one thing to notice here is that if I write length of A concatenation with B, let's say that this is another program I could write. Does this do the same as that one? It's the same exact program, right? Except I'm not using a let binding here. It's kind of one step simpler. Of course, if you don't use let bindings and if you don't name intermediate things, as a programmer, things become really confusing. So one reason to have this let form is just to make your programs more understandable. In this case, I'm just calling this thing x. So it's not really adding anything. I guess that would be a simpler version of the same program. But let's try to type this. So how do we derive a typing derivation for this? The first rule I want to use is the let rule, because let is this thing on the outside of the program. And that rule says that I have to have two subderivations. I have to prove that this E1 has some type, and then under that assumption that X has that type, E2 has a certain type. What type is this program going to have in the end? What kind of thing does it produce? Number, yeah. Okay, so now I have these two subderivations. One of them is reasoning about concatenation. And what type is the concatenation going to have? String. Now there's two hypotheses where I have to prove that A has type string and B is type string. I'm just going to sort of abuse notation to save space and say, basically these are both axioms. I should have written them side by side. In fact, I wish I could change it right now, but sorry. Now here, basically now I've established that this X is going to have type string, right? Because that's the type of the first sub-expression. So I extend my typing assumptions and say X has type str. And now I have to type length. And we've already said that length is going to have type number. I should say these are the stir rules. So what do I write as a hypothesis here so I can be done with this derivation? You have to remember what the typing rule for length was. Maybe I can write that up here. It's the length rule. So I want to apply this rule because length is the thing that I've got here in the conclusion. Basically, now I have to show that this sub-expression, which is x in this case, has type stir, right? How do I show that? Well, it looks exactly like this, right? This rule that I wrote. One of many variants of the same rule, which is the variable rule. So I'll just call it the var rule. No, I'm done. That's an axiom. There's nothing on the top of those rules. This one has this thing on the top. And if I wanted to be really, I don't know, show like all these details, I guess I could. I could say, oops. That if I treat this whole thing as a map, and I map x, that gives me stir. Right. If you treat this thing as a map, and I say, what does x map to in this map? Oh, it's right there. X maps to stir. So this whole thing is equal to stir. Any questions about that? So this is an example typing derivation. Yeah?
What was the var rule that you referred to?
Oh, right. I forgot to name all these rules. So this one should be named num, stir, and all these rules are different variants of the var rule. Depending on which textbook you look at or which paper you read, people will do all these different things, and they mean the same thing. Okay, so any other questions about the typing derivation? Yeah.
So you call that paradise map, right?
These parentheses? Yeah, so in most of the languages we look in this class, parentheses will have no meaning. So people can just put parentheses around things to make things more clear. Like, if I wanted to put parentheses there just to make it really clear, I could do that. So it's confusing because the last thing we looked at was all these parentheses where the parentheses are special, but I just put parentheses around things to make things more clear. So here I'm saying I'm applying this context as a map, so I just wanted to put parentheses around it. I don't know if that answers your question. Are you asking like why I put parentheses around this or what I'm doing in this line? Oops.
I'm doing this line.
Oh, wait, undo. Sorry, what was it?
What are you doing in this line?
In this line. Yeah. I'm trying to apply basically this first version of the rule that I wrote. So what that rule says is that I should take this context as a sort of map, as a function, where it sends variables to types. But in this case, the context that I have is this whole thing. Right. And I just wanted to put parentheses around it to make that clear. Yeah.
So the reason we need this gamma context is because we have like the let expressions that can bind.
Right.
Okay.
That's right. In general, I mean, we'll look at better or more interesting languages where there's going to be more cases where variables get introduced. In this language, there's only one case, which is the let case. Yep. If we didn't have the let case, I guess maybe your question is, if we didn't have the let case, would we even need these turnstiles everywhere?
Yeah.
We wouldn't. They would basically be empty because there's no variables.
Well, turnstiles were the thing next to that.
Ah, thank you. I circled what I meant to say, but I meant to gamma these contexts. Yeah, thank you. Yeah, term styles are just inert symbols that don't have any structure to them. The contexts have this structure. Any other questions about the typing derivation? Yeah.
Just I confuse a little this gamma with what we use for memory map, that we map a variable to the value in memory. So what's the differences?
Yeah, that's a good question. So in a lot of languages, variables are mutable things. They sort of refer to values, right? And you can change their state over time. Are these variables like that? No. They're just names for expressions or names for values. So this is like a more mathematical language where the variables don't change state over time. In other words, in this program, like once I've concatenated these two strings together and I call the result x, x will always be that concatenation for all the time. It's never ever going to get mutated and change to something else. Later in the course, we'll talk about programs with state and mutation, but for now, there is no state or mutation. And the other important point is that here we're mapping variables to types. So it's not even quite like state because types are supposed to be invariants. A variable is supposed to have the same type over the whole course of the program, right? So you can think of this as basically being like fixed. It's not changing over time as the program runs. And maybe it's getting more bigger and more extended, but it's not getting mutated. If x has type tau, x will never have type some other type that's not equal to tau. Any other questions about the typing derivation? Or about the rules that we talked about? No? OK. So in that case, let's just get a quick flavor of what the dynamic semantics looks like. Well, I guess there's all these other properties to talk about first, but I think maybe it's more interesting just to skip them for now. We'll come back to them. Okay. So probably in some computer science course, if you've taken a course about automata, this definition is going to look somewhat familiar to you. So what the author is trying to do is define, in a very general sense, what a transition system is for a formal kind of programming language. So there's a bunch of properties, he says. First, there has to be a notion of what a state in the transition system is. Then a notion of when that state is final, like when are you done running the program. What states are initial, like where do you start running the program, and then how do you step the states. That's just kind of like setting the context here, but this is the important bit. So let's write down our programming language again. These are exps. Okay, so the states are, in this case, and for this programming language, are going to be these expressions. So we might start with the expression we just typed and try to run it to get some value at the end. By the way, what should the answer be for that program we just looked at? I concatenate two strings of size 1 and then take the length. It should give me the number 2, right? So the point of this transition system is to basically tell me that that program evaluates to the number 2 somehow. OK. What we're going to do, though, in general is define a kind of notion of a single step, an expression becoming another expression, like this. So we'll define that, and then based on that, we'll define this notion of running the program until it can't run anymore. Or until we're sort of satisfied, we don't want to run anymore. So this is like the reflexive transitive closure of this single step. There's 2 rules. call this the reflexive rule. So if I have a program, I can say that it runs in 0 steps to itself. That's what star typically means, right? Is you're allowed to relate the thing to itself. Okay, that's the reflexive rule. And then there's going to be a kind of transitive rule or a take a step rule. So if E1, if you want to say that E1 eventually evaluates to some program state E3, we can prove that by showing that E1 takes a step to E2, and that E2 in 0 or more steps to E3. Maybe I'll call this the step rule. So with these 2 rules, I basically define the reflexive transitive closure of this. And I'll call this relation the step relation. Does anyone recognize these? Yeah, go ahead.
What's the meaning of the star?
Right. So one purpose is just to differentiate these conclusions from that conclusion. So intuitively, what I'm saying here is I'm going to take the program 1 step into the future. And we haven't defined that yet. But given that, star is going to mean take 0 steps, 1 step, 2 steps, 3 steps, any number you want. 0 or more. There's another thing he does in the book, I think just below this, where he says, rather than not specifying how many, you could actually index this arrow thing by some natural number n, and then you call this the 0 rule and the successor rule. So it's the same idea here where I would just write, in this case I would write 0 instead of star. Here I'd write 1. Here I'd write n plus 1. Plus 1. Sorry, I goofed that up. That should just be n. So this is the 0 rule. 0 steps are taken. This is the sort of suck rule where I take 1 step, then some more steps, and then I've taken 1 plus that number of steps. Okay, blah, blah, blah. Let's go to the actual interesting rules. So now we're defining the single step relation. So if I have 2 numbers and I add them, that's the way you evaluate plus. Maybe So what is this rule for? I can rewrite it to be bigger. Maybe. Is there a way to oh, wow, that actually works. Wow, that's awesome. Okay. It's fuzzy, but it's much bigger. So maybe look at this rule first. Does this make sense to everybody? I mean, he's playing this game where he's not actually defining what addition means. He's just assuming we have a definition of addition. We did that in the first class, so it's not that important. But somehow you've defined what natural number addition is. And then for the programming language, when the programming language adds 2 numbers, you just defer to that definition, and that's the answer you get. But why do we need this rule? I can ask it a different way. Suppose this is my program. Let's say I'm trying to run this program. I'm trying to say it steps to, well, eventually I want it to step to 6, right? And if the programming language is good, then I should be able to derive this somehow. So if I just try to apply this rule, and I'm not writing the num parts in the brackets because I think that's kind of noisy, but it doesn't apply, right? Because for it to apply, this would have to be a number. Let's call it n. This would have to be some other number. Call it n1, n2. But this isn't a number yet, right? This is the addition of 2 numbers. I haven't evaluated that part yet. So what this rule is saying is, if I have some expression here, and that expression can take a step, then I can basically plug that new expression back into where the original one was. So how would I apply that principle here in this case? I basically want to step n1. Well, this isn't an n1, right? This is an e1. I want to get this to be in natural numbers. So I can say, well, 1 plus 2 takes a step to 3. That's by this first rule called the add rule. And then let's say that I want to be more specific here about this takes a single step. So what is this step 2?
3 plus 3.
3 plus 3, yeah. And now that's just using this, I'll call it the add 2 rule. It doesn't have a name right now. Now if I'm trying to prove this whole thing eventually goes to 6, this would have to be some part of some larger derivation. In the larger derivation, I'm taking multiple steps, right? I'm not done running the program because I still have to add these 3's together. So I need to take yet another step. Eventually I want to show this goes to 6, but I'm running out of space, but there has to be another derivation here where the conclusion of the derivation is what? 3 plus 3 steps to 6. So in this case, I'm using the suck rule that we talked about, where I'm taking multiple steps. The first step I'm taking is adding 1 plus 2 to get 3. And then 3 goes in the place where 1 plus 2 was. And now the next thing I want to do is add these two 3's together and get 6. That just goes by the first add rule. And this goes by the suck rule. And eventually the last derivation we have is that 6 steps to 6 in 0 steps. The last thing you always do is say, well, I'm done running the program now. So this is kind of a messy version of what the tree should look like, because I ran out of room. Does anyone have any questions about this? I can write it out more carefully if that would help.
Yeah, that would help.
Yeah, okay. So this is ultimately what I'm trying to show. 1 plus 2 plus 3 goes to 6. And it's going to require multiple steps. So we have this multiple step rule that says that I can take a single step and then continue stepping the thing. So that's my single step that I'm taking. And the way I'm taking that is by applying 2 rules. I think I called it add 2 and add. I'm sort of realizing this would maybe less confusing if I change the second 3 to a different number, like 4. Just so we don't have like multiple 3's, it's a little confusing. Okay, so I want to step 1 plus 2 plus 4 to 7. It's going to require multiple steps. The first step is changing this 1 plus 2 to a 3. And I justify that with this rule and this other rule. I have to use these 2 rules together because the 1 plus 2 is kind of deep inside of an expression. I have to go and find it in order to do this add. Okay, so now I've got the program state to 3 plus 4. So I can try to prove that 3 plus 4 steps in multiple steps to 7. And if I do that, then I'm done. Does everyone see that I'm done if that's the case? Right? So what should I do now? I should take one more step, right? So 3 plus 4 steps to 7. That's by this single original add rule. And then I have to show that 7 steps in some number of steps to 7. And we have an axiom that says that. We have an axiom that says, write E. E steps to itself in 0 or more steps. There's a rule that says that, right? So that's the whole tree. That's the whole derivation tree. I should call this the successor rule, and the 0 rule, or something like that.
So
Yeah.
how many steps in total?
Yeah, how many steps did I take? It looks like I took 2, right?
So add and add 2 are 1 step, right?
Correct. Yeah, that's right.
So it's a little bit confusing.
Yeah, it's a little confusing. So add 2 is part of this whole step where I'm stepping 1 plus 2 plus 4 to 3 plus 4. And I didn't need it here because there was no outer expression wrapping this addition I was trying to reduce. Anyway, I think we have to move to office hours now because we're out of time. We have to let the next class in. So I've got office hours in about 15 minutes upstairs in ECCS 122.